As I was saying, I've spent quite some time with turbulence. So I would today like to convince you that turbulence is interesting and useful for physicists and engineers. So the structure of the talk is quite classical. I'll start with some introduction and basics. So we'll talk about what has been done in the past. With the state of the art, we'll talk about what is being done at the present. And with evolution in the field and career paths, we'll talk about the future of turbulence and the future of engineers who are studying turbulence. Just to give you an overview of the time distribution, the first 3 points will cover 80 to 85% of the total time, and then in the rest of the time, we'll discuss the further points. Right, let's start. So in the graduate fluid mechanics books, how they introduce turbulence is with the Reynolds dye experiment, which was done almost 130 years ago now. So what Reynolds did was he introduced a dye in a flow in a pipe flow in which he started increasing the velocity gradually. The flow was nice and smooth, so the ink would follow a straight line. However, when he increased the velocity in the pipe, he started seeing some chaotic motions, and with the help of the ink, because the ink follows the motions in the flow in the pipe. When you observe these motions with an electric spark, you see some vortices, eddies, some blobs of this ink going around in an apparently chaotic motion. So this is where the story about these chaotic motions, it kind of stops in the undergraduate books. And personally, this quite disappointed me. I wanted to learn more about them. So today we shall go more deeply into these random motions. Oh, by the way, fun fact, Osborne Reynolds Day is still celebrated in Europe. Last year it was in University of Manchester, and I was lucky enough to participate. I had a look at the original experimental rig that they preserve at the University of Manchester. Quite interesting. Right, okay. So turbulence, everyone has seen it in form of smoke coming out of the chimneys, in the rivers, in the oceans. And the lucky ones, pun intended, might also have felt it on a flight. You have to suddenly tighten your seatbelts. Everyone sees it everywhere, but how do you describe it in terms that are useful for physicists and engineers? So let's go step by step. First of all, if you play the video of this smoke coming out of the chimney in your mind, you could instantly say that, okay, it's very time dependent. All the motions that you imagine are time dependent, and they look apparently random in space as well. So we can say, okay, the motions are unsteady as they evolve in time, and random if you look at an instantaneous picture in space. What else can we say? So you see these blobs of eddies or vortices, one could call them. If you zoom in a bit, you would see this big cloud, which looks like it's a blob of certain kind of motion. And then you can see smaller ones with my indicator, and you can classify. You can say that, okay, right, I see some kind of blobs of motions which are of different size. So you can say, okay, there are various sizes of eddies in this flow. Right. The next step for engineers would be to simplify this flow. And how do they do it? So if you put a probe, a velocity probe at some point in space, you could register the velocity at that point, which is shown in the graph. On the x-axis is the time. And you can, if you don't need all this chaotic information, you can just average it out. and you call it the averaged velocity U bar. And this is a quantity that is usually important for engineers. So we'll talk about this more as we go on in the basics. We have seen some observations. We have made some observations, and Hinze actually put all these observations into a proper definition where he says turbulence is an irregular condition of flow in which quantities show a random variation in time and space. So this is what we observed. So that statistically distinct average could be discerned. And we saw that we can get an average out of all these details of the flow. Right, but as an engineer, why should I care about all this information? And why should I care about turbulence in general? First, in fluid systems, turbulence is almost omnipresent. It's present in most of the fluid systems that you would encounter. And I'll give examples in the coming slides. And second, because it's everywhere, its understanding is vital, is critical in design and optimization of systems that have any kind of fluid interacting with them. Whether you do measurements, whether you study those systems with measurements or with CFD. Okay, let's go a bit in more detail of the first point. So I would like to give you an example starting from the astronomical scales. So let's have a look at the surface of the sun, and you would start seeing the similar structures that I was describing before. So for example, you have a bigger vortex, and inside there are smaller and smaller vortices. And this pattern is everywhere, wherever you see. So for example, on the top right corner, you would see similar structures. So this is the surface of the sun, the motions on the surface of the sun. Then you can come, so similar things are happening on gas giants such as Jupiter. And one could do a quick Google search and see all those beautiful patterns with the great red spot going around. Coming onto the Earth, I found this really exciting animation on the NASA website where they follow the currents in the oceans. Here, I would like to start with this Gulf of Mexico, and this is the Gulf Stream. And I'd like to just play it and show you how the currents in the oceans are carrying fluid from one place to the other continuously. On the top right, you would see that the time scales are in days and months. So you see all these vortices shed from the continent of Africa, how the waters are all interconnected. So for example, from Sri Lanka, the south of India to Africa, and so on. And you would see these are similar type of motions that we have made observations for in the past slide. Similarly, if you come towards the engineering applications now, in turbomachinery, for example, in transport, in automobiles, ships, rockets, everywhere you can imagine. So I'd like to give you an example on how in flight and turbomachinery, turbulence is important. So as you could imagine, this is a wing and an aero engine, which is structured into the wing. Now, looking at various aspects. So inside the combustor, high temperature gases are formed, and for those gases and the metal surfaces to coexist, you need to have efficient heat transfer. So people study heat transfer. So here they are studying heat transfer at the trailing edge of one of the components. Then you need to have efficient internal cooling of the components as well, where you have highly turbulent flows. Then, for example, here is a compressor blade. You see that complex motions arise in these configurations, as you can see. Then on a similar blade, you would see that the flow goes from laminar to transition to turbulent, and these forms challenging applications in engineering. Here they're showing the mouth of the engine. So this cross section here is coming from the cross section of the inlet of the engine. And if you have crosswinds or you have landing configurations, you can have massive separations in these configurations, and you have to see the system response to all these conditions. Now, people who are more excited about automotives is the famous Y250 vortex, which keeps the turbulent flow coming from the front wing away from the body of the car. So this is an extreme example in the automotive industry where you have this highly optimized airflow management, and all this involves the knowledge of turbulence and the coherent structures. All right, so now I would like to come to a scale that is the smallest. So we started from the astronomical scales towards the Earth scales, then the engineering application scales, now to the insect scale. People doing CFD are studying this kind of problems as well. And here I would like to highlight that you see similar kind of patterns, like where you see a bigger vortex and then smaller and smaller vortices. From an engineering point of view, if you are a CFD engineer, your boss could ask you for key quantities like coefficient of lift, coefficient of drag. If you're studying heat transfer, Nusselt number. If you're studying mixing combustion, then people might ask you, okay, what is the mixture fraction distributions? What is the temperature distributions? If you're studying spray, there could be spray characteristic questions. And then some people study aeroacoustics. Here you would have to come up with an answer of what is the sound pressure level at a certain location from a certain aerodynamic device, and so on. Now, many applications also involve flow control. Here, for example, in airfoils, you would like to keep the flow laminar for in some area and then turbulent in some other area. So for this, you have vortex generator devices, suction devices. In automobiles, you would like to minimize the noise, say, for example, the side mirror. And all these designs involve either measurements or CFD based on turbulence models. Especially for CFD engineers, understanding of all the physics behind turbulence might not be that interesting, but at least the understanding of the turbulence models could be very useful. So because now we are going towards CFD and turbulence models, let's look at the basics a little bit so we can talk more easily. So this is the governing equations for Newtonian fluid and incompressible flow. So the first statement is just mimicking the mass conservation. The second one is mimicking the momentum conservation. Here, I would just like to quickly say that use the velocity vector, P is the pressure, and mu is the viscosity of the fluid. These equations were posed almost 200 years ago, but still the challenge is that we don't know the analytical solutions for these equations. In fact, we don't even know the conditions for which the smooth solution to this Navier-Stokes equation should exist. And it's a Millennium Prize problem in mathematics to date. From the physical point of view, people ask, is it possible to make a theoretical model to describe a turbulent flow with its internal structures? And again, it's an unsolved problem in classical mechanics. So we don't have any analytical solution for the equation I showed you. So what are we doing since last 200 years? What we are trying to do is trying to break up the problem, trying to come up with empirical models and basically the best we can do without solving the equations analytically. So let's understand a bit more the terms in this equation. The first term, as you can see, is the derivative of time. So it tells you that there is the hidden meaning of unsteadiness in this term. Then there is this more complex term, which involves the product of velocity. I call it the inertia term from the physical point of view. There is the gradient of pressure. We'll talk about it later if we have time. Then is another important term, which relates to the viscosity. So the internal friction in the fluid. I call it the friction term. So let's see what these terms all do. So starting with a very basic flow, it's just a flat plate. The fluid is the flow is coming from left to right. So in the beginning, in the upstream part of the plate, there is no visible unsteadiness. The flow is quite smooth. It's laminar flow. In this regime, the friction term dominates. What it's doing is damping out or smoothing out all the little instabilities that are occurring. As we start going towards this region, towards the transition region, you could see there start to appear some two-dimensional disturbances, which are then becoming more and more complex in structure. And at some point, the turbulent spots, the so-called turbulent spots, appear, where these two-dimensional instabilities are now becoming three-dimensional. And eventually, we just have a forest of vortices or eddies. And in this fully developed turbulence flow, there is total domination of the nonlinear or the inertia term. So what we learned is that when the inertial term dominates, there is highly likely to have developed turbulent flow. So let's see how we compare these two terms, the inertial term and the viscous term. So you can write the term as they are and try to do an order of magnitude analysis. So what you do here is you put density as it is. You know that there are two velocities and a differentiation, a space differentiation of the velocity. So you have the u square and then a space coordinate. Similarly for the viscous term. And to see which term dominates and vice versa, you take the ratio. And at this point, some people might be recognizing this ratio, which is the Reynolds number. And we have learned in our graduate book and undergraduate books that the flow becomes turbulent when the Reynolds number is greater than some critical Reynolds number, which is usually 2000 for pipe flow, simple pipe flow. So Reynolds number can be interpreted in this way, that it's a ratio of inertial and viscous forces. Okay, so in the beginning I was talking about scales, and then I came to this Reynolds number. So let's now connect them a little bit more. So I said that if the Reynolds number is large, it means that the inertia term is large and the viscous term is relatively smaller. But it's not the case for all the scales of motion. So for the bigger scales that you see here, indeed the inertia term is high. But if you go to smaller scales that you cannot even see here in this picture, at the smaller scales, I would like you to imagine that because there is motion between the particles now, the viscosity diffusion dominates. The viscous terms dominate. So in fact, how it happens is that this apparently random energy, it is starting from the largest scales, and then these largest scales they break down into smaller eddies, until they come to the smallest vortices that are possible in a flow, where the viscosity then dissipates these vortices as heat. And this is known as energy cascade. There is a little poem about this energy cascade, which was written in 1922 by a famous scientist. I would let you enjoy this little poem by yourself. Basically says the same thing, that big worlds have little worlds that feed on their velocity, and these little worlds have even lesser worlds, and so on to viscosity. So yeah, beautifully done.